You are the pioneers. With your visions, your ideas, and your passion to make things better. And we are the ones who protect you from pitfalls. We are by your side whenever needed as a true fellow. Reliable, pragmatic, realistic. Together we make your product come alive. Imagine you enjoy improvement. Process Fellows.
All right, then we're gonna start. So a very warm welcome from our side, from Process Fellows, to our today's webinar called System Engineering and Why the Heck Do We Need This? From the introduction on our website, we had some very, let's say, provocative words to that, and some concerning the challenges this might have. And we're gonna talk about this later in technical details. But before we come to the actual, let's say, content presentation, I want to shortly promote some of our next trainings, introduce our company, and have some organizational aspects. So as you can see, we offer various in-text trainings in the next, let's say, upcoming period. And all of them here are already guaranteed. So if you have, if you're interested, for example, in becoming a competent assessor regarding the old model, the 3.1 version, then you're very welcome to attend the competent assessor training. As well as we offer the first upgrade training here, which is in April. Then we do have the provisional course as well, and automotive spice for cybersecurity training. And if you really enjoy this webinar, we also have a deep dive into system engineering, and we have our own training. This is in June. So I hope all of you, or at least a few of you, already know our company Process Fellows. So we're mainly operating in the automotive sector, and we have various fields of topics we cover. So our most, let's say, present topic is, of course, automotive spice. But beside automotive spice, we also have other topics, for example, project management and agile development methods. And also we have, of course, cybersecurity, functional safety, and let's say mechanical and hardware spice. So we offer different topics here. So basically there are four, let's say, operating areas we have. Of course, we are very present when it comes to assessments and gap analysis for supplier sides. And also our next big topic, let's say, is training. So we do have the official in-text trainings, which we saw on the first slide, but also our own development trainings. And the middle ones are consulting and coaching, which we do very passionately and do a really deep dive also, and training on the job. So this is something we offer here. When it comes to the organizational of this webinar, I just want to point out a few things. Please be muted through the presentation. You will have the chance at the end to ask some questions, so we will have there a time slot. You can use, during the presentation, you can use the F&A, or in English Q&A slot, which we're gonna collect and try to answer at the end. So if you have a question, intermediate, let's say, you can type your question in, and then we're gonna come to that at the end. This webinar will be recorded. I already started the record, the record at the very beginning. None of your personal detail will be displayed or published. The training or the webinar will then be later uploaded on our website. This will take around, let's say, 1 to 2 weeks. And also the slide set will be uploaded to the website and on YouTube. So coming to our colleagues, I'm not doing the webinar alone. So with me is my colleague Sebastian Keller. He's a certified provisional assessor. His interest fields are automotive spice, focus on testing, project management, and functional safety. And he really has a passion for testing processes and process improvement. Let's quickly come to myself. I'm also a provisional assessor. To be fair, by now, I'm on my final way to become the competent assessor. And my interest fields are, of course, automotive spice, project management, system engineering, functional safety, and cybersecurity. And with this said, I would like to hand over to my colleague, Sebastian.
Yeah, thank you, Alex, for the introduction. And from my side, welcome to everybody. I will start the webinar now. Just a question. Can you see the slides, the first slide?
Yes.
Okay, so
Yes.
I think we can start now. As Alex already mentioned, we are asking the question, why the heck do we need systems engineering? And the first thing I would talk about is, where do we come from? What was before approaches like systems engineering? So the first thing where we came from in the early development of, let's say, in the automotive or in general in the software, mechatronic, electronic development is we had things wrong with my presentation. Okay, now it's working. In the early stages of development, we had some kind of pioneers of development. They were not a systematic approach. They were just smart inventors that developed or thought about new ideas and developed them. In most parts, it was possible to invent a component by a single person, and in the last decades, it was a possibility to do so because we had in very much of the components a clearly defined function, no cross functionalities, no complex systems. So it was possible for one person to supervise the development of a component itself. And in very much of the developments, there was a very wide solution space. So the inventor had the possibility to think about how can I do it and use all for him possible ways to solve the problems to get to get to this component. And that took, of course, a long time. In some cases, in the early development, there were inventors that were developing a component or a system or something for their whole life, for example. It was the use case that you just tried to get a prototype, that you did some trials, and when it worked, you used it, you improved it. But in the present, that's not possible. What is the development nowadays? What are changes from the early development to the actual development? We got way shorter development times. I think every one of you knows the customer with his milestones, and the worst thing you can do is to not achieve a milestone in time. I think that's one of the most important things. As I mentioned, in early development, we got components that had only one functionality, only one sense. And in the actual development, we got cross functionalities. We got components with lots of functionalities. We'll get to some examples later on. Also, we got much more interfaces in the components. We got interfaces from software to hardware. We'll see later on to mechanics, from hardware to other hardware, from software to other software components. There are lots of interactions within only one ECU or between ECUs, for example. And therefore, we got in the last decades a highly distributed development. There are software teams all over the world with experts all over the world, and it's not only one person at one site or one team at one site who is developing. It's just all over the world. Of course, with shorter times, with higher functionalities. We got a high pressure to hold the cost on a level that's acceptable. The cost can't explode. And as I mentioned before, we got classical mechanics development. In addition to hardware, software, so it's getting really complex systems with different kinds of structures we need here. So hardware development, software development, mechanics development is based on different approaches because we got this in history. Yeah, one of the examples we can use is the development of aerospace. What we see here is the so-called Europa rocket or Europe rocket. It was one of the first approaches of the European countries to get to a carrier rocket, and they tried to distribute the development too. So there were different countries that were developing it. In general, the main parts should be developed by Great Britain, France, and Germany. So these alone these three countries got different languages, got different units, like the metric or the imperial unit. In the first step, they tried to put the work packages according to a country, not to knowledge, but to country. Every country should get one work package. And that was a big failure. So the Europa rocket, I think, didn't fly successfully at once. And what did they do? They had to get to a better development approach. So what did they change? They already got work packages, but in this case, they screened who has the experts for the work package. They coordinated everything from a central position, and not everyone does his work package without coordination. They started to use the same language for descriptions for the development. And of course, they used the same units. And that led to the Ariane rocket. I think everyone knows it's one of the most successful carrier rockets in Europe or even in the world. And this was an example where the development had to use a better approach, because we got a very complex system with different parts from different countries. And as I mentioned, the Ariane was a big success later on, and it's still one of the rockets that's used as carrier. Another example is, for example, the radio in the automotive sector. As we see, in the former times, we got only a radio that made some music or some sound. And in the past years or decades, the functionality was growing from just a radio to being a whole infotainment system. And the whole infotainment system is way more than just a radio, or for example, if you go for videos, for example, it's a steering unit for nearly the whole vehicle. You can use it as radio, but you can use it to screen all of the sensors of the vehicle, all of the surrounding of the vehicle, to adjust whatever you need in the vehicle, to communicate with everyone in the vehicle, or like meetings or something like this. That's the part of the functionality. The functionality in the last decades of just one component was very much growing. And another of the points is the complexity. I think a radio is not this complex. It has just a function, and it has just some transistors. Maybe there's no software in it, for example. And in one of the present systems of the infotainment systems, it's not just a system. It's a kind of system of systems. There are very much ECUs that has to work with lots of sensors in the car, with lots of communication interfaces, with hardware interfaces, with mechanical interfaces in the car, with some actuators in the car. And so the complexity of those systems has increased very much the last years and the last decades. And I think with autonomous driving, for example, it will increase way more than the last years. Another example for the challenges in the last years or in the last decades is the topic of the distributed development. I've already mentioned that in the last decades, the development was distributed all over the world. And if you see here, for example, in the 1970s, it's just an example. We got a component that was developed by a supplier, a tier 1 supplier, for example, that had a project at his site with his project team on site, and that was a kind of easy development because everybody was at the site and it was one team and no interfaces, nothing around. And in the years after this, it started to grow bigger and bigger. Companies started to grow bigger and bigger. You had to get experts from nearly all over the world. And so the companies started, and in this case, the supplier had, for example, it's the same supplier, but he already had 2 locations, maybe one in Europe, maybe one in Asia. And nowadays, it's way more distributed. We got a tier 1 supplier, for example, that can have a tier 2 or even a tier 3 supplier. We can have several software components from all over the world where teams never meet and only got their interfaces online. So it's way more distributed the last years or the last decades than before. And that's one of the great challenges to coordinate those teams and those development all over the world. Yeah, as I'm talking about interfaces, it's not only interfaces between teams, it's interfaces between different levels, for example, or different categories of development. As we see here, we got several interfaces between several, let's say, development steps, for example. We got the system development on the higher level. That has interfaces to a software development, maybe to a hardware development, maybe to a mechanical development. But even within one level, there can be some interfaces like the software-hardware interface. And I don't speak from the interface, from the physical interface. I'm speaking from the development interface. So they have to be coordinated so that the software is running on the correct hardware, for example. The hardware can be mounted within the mechanical components. So there are lots of interfaces that have to be coordinated too. And that's not only for the pure development disciplines, that's also for disciplines we see down here, for example, for the management and supporting processes like project management, quality, changes, problems, and so on. There are lots of interfaces that have to be managed. And this is one of the other big challenges in a complex development world. Yeah, and now I got a question. How to solve this? Alex, maybe you can help there.
I'm pretty sure I can. So let's come to the next slide. All right, so this is kind of a wrap up what Sebastian already presented. So we have various challenges in not only in the automotive sector. So system engineering, the origin of system engineering comes really from space engineering, but it can be, let's say, found in various domain industries. For example, also railway or medical systems. And on the rest of the webinar, we concentrate mainly on the automotive sector. But these challenges, let's say, I'm pretty sure they reflect to all of these industries. So what we have seen, the complexity is increasing over the time. We have some certain technologies which comes to place. For example, in the automotive industry, we have nowadays the artificial intelligence, but also functional safety and cybersecurity aspects. We need to make sure that our system is secure by design, which is another requirement here. We have seen that in early development, the domain development was pretty mixed. Now we have some specialization of domains. So we have the really software experts, we have the hardware experts, we have the mechanic experts. They're real experts in their disciplines. So this has also changed and also an impact. And of course, we need to bring our products faster and cheaper to the market. This applies to all industries. And of course, for example, the change from classical project management to agile project management. And sometimes we have hybrid structures. So these are all aspects which comes into place. And the solution to that is systems engineering. Not the only solution, but it is a solution. And why is this? We're gonna highlight in the next slides. So we call systems engineering as an umbrella. We have various disciplines in the whole, let's say, product development. So typically we have our architecture design, we have some risk management which come into place. Then we have the functional safety, for example. Of course, we need to consider our quality standards. Then we need to make some thoughts and some approaches about the integration of the system. Requirements engineering is a big topic. So what I want to say is that we have very different disciplines here, but all of them needs to interact in a certain way to bring a really successful product to the market. And this is why we illustrated here the umbrella. So you can really see systems engineering as an umbrella, and it is an interdisciplinary and holistic approach, which helps to really realize successful systems here. And of course, always the customer needs is in focus. And due to the fact that we need to bring products shorter to the market, we need to try to get the functionality first. Big impact is the feature-oriented development in the automotive industry. So we really need to concentrate on the function first and to handle also the complexity. System engineering here is communication. So I like to compare the systems engineer to an orchestra. So the systems engineer, let's say, is the musical conductor and needs to control every music instrument. If you would like to compare, this is also the same topic here with the certain disciplines. And of course, we also have a standard for systems engineering. I just want to mention it here. We have the ISO 15288, which is concentrating on system lifecycle processes. But we are not going into deep in that standard. So what are some main activities of system engineering? And this is really high level, but I would really want to show it to you quickly. So a typical method or activity in system engineering is to identify your system levels. Where are you operating? As well as structuring your system. So you need to identify your components and your interfaces. We will have some examples on the next slides. And of course, very important topic in the whole meaning of system engineering is the communication aspects and the communication between different domains here. So typically from our experience as a consultant, when we come to suppliers or even some OEMs, it is very challenging to distinguish between the system level, so the real different system level. Of course, we have at a certain point of time our overall vehicle system level in the automotive industry, and at the lowest level displayed we have the hardware, software, and mechanic domains. But between that, we have various subsystem level, and it is often difficult to really find the organization and the product at one specific level and the real target level. In automotive spice assessments, for example, this is let's say a short excerpt here. In automotive spice assessments, if we have some various subsystem level and some different product parts, we can make some instances to rate them. But here in this example, I just wanted to highlight that, of course, we have the vehicle, for example, then we have our powertrain system, which is the first subsystem level. And this subsystem level can now depending on your complexity and how you want to structure and develop your product, can have a variety of subsystem level, which you decide and which fits best to you. In our example, we only have here 3 subsystem level, which is just to simplify it. So the next one would be the transmission system and the steering system. And the transmission system, for example, divides itself into gearbox and the differential. And at a certain point of time, we come to the level where we can say, okay, this is really now software, hardware, mechanic parts, the lowest level here. Coming to the next activity, sorry. So the next activity is also very important one. It's the correct identification of component and interfaces. So if you take a look at this would be also the subsystem at the door system. The door system consists of several parts. You have the window, then of course you have the dotted line here is the system context. So really how the door system is interacting with your environment. You have the user, but you can also have an external control unit which controls the door system. And this consists of, let's say, switch, control engine, and the lifting device. And on that level, you can already tag, let's say, or make your thoughts what unit, what block, I would say here, can later then be done by hardware, by software, by mechanic. So this is about identifying what components do you have, if the components can be realized by hardware, software, mechanic, and what are the interfaces to each other. So this is another big and important aspects of system engineering. And another activity is the communication. So Sebastian already mentioned it earlier. So I would say pretty every system consists of various levels. We have, of course, the overall system level, but then we have the software domain, the hardware and the mechanic domain. And as a system engineer, it is important to have a look at the interfaces and to really understand the needs of their specific domains. And sometimes to, let's say, translate between domains and to map the requirements of each other to really get the complexity and to develop the product. And this is a very crucial thing, the domain communication. We can see it here, for example, the hardware-software interface. This is something which comes into place, for example, especially when developing functional safety, but also the agreements between the different domains. We have several bumps for hardware, mechanic, and also software. And for the integration aspects, you really need to communicate between the domains. So what can be, or what are the competences of a systems engineer? And these are some aspects what, from our understanding and also from the literature, is that a system engineer needs to have some certain skills. So, like I said, if you compare it to the musical conductor of an orchestra, the system engineer needs to have a good understanding about the product, about the overall system, and the system engineer needs the big picture view. So to really understand what is going on with our system. As well, the system engineer needs to concentrate how several system singular elements change over time. As you remember, we have the ISO standards. It's about system lifecycle processes. The system lifecycle is not only the development phase, it's also when it comes to decommissioning and if it's in the field. So we have a whole lifecycle, and this needs to be also maintained. What else is there? So the system engineer needs to concentrate on the structure of the system and also to really identify what my system structure can interfere with a certain system behavior. So this can also have an impact. Another good example is that we come to that later when we talk about model-based system engineering, that we have various viewpoints or different angles to look at your system. So you can investigate your system, your target system, in terms of, let's say, requirements viewpoint, in terms of functional viewpoint, or also technical viewpoint. So these are some viewpoints which comes into place to really understand the complexity and handling also the complexity. As a system engineer, you should be aware of short-term consequences, but as well as long-term consequences. So I already mentioned it's about bringing the functionality as early as possible, but you need to consider it as a whole picture. So it's not very efficient if you only do it short time, but forget about the long-term consequences. So you really need to consider both. And that every action you take at the system will have an impact on the lower system levels and also have an effect. So let's point out some responsibilities and some solution spaces of system engineering. So the responsibilities of system engineering is aspect number one, communication. So you need to balance between domains. You need to also discuss with them. You need to come to an agreement. You need to talk about some certain aspects you need to discuss with them. So it's really about balancing the conflict between some domains to get the solution. Also, we need to have an efficient and goal-oriented management. This is also, of course, very important. When we're talking about the long-term effects, we need to have a strategic thinking. So in the classical system engineering, you really develop a systems engineering management plan that you consider the long-term aspects as well, not only the short terms, and strategic thinking. Strategic thinking can also be that you have, of course, that you have, for example, an architecture criteria that you want to develop your system or your products, let's say, reusable. This can be also a way of strategic thinking which comes into place here. And another aspect, the system engineering should bring knowledge to all levels. So what can the system engineering contribute to? So we can come from an organizational point of view and bring some specific methods to the teams on the, or even deploy it on the organizational level. Methods can be, for example, model-based system engineering, usage of SysML. So there are various methods here which can be distributed along the organization and the project. Then you can also establish some teams. So in really high, complex and big projects, it is beneficial to have system engineering teams, which really have the general overview, the interdisciplinary overview here. And another aspect which we also always see is if you develop a generic or platform development in terms of reusability, generic architecture. This is also something which comes into place when talking about system engineering. It also has a good, let's say, good chance to investigate your toolchain. So if you later on decide on implementing model-based system engineering to store the information within one model, it is beneficial to have it all in one model, and then you don't have the tool, let's say, interruptions each time. So there are some vendors which offer some MBSE tools and to improve the toolchain. For this webinar, we had a look at the automotive industry and what is the demand of system engineering. So, and we come to the conclusion that it is increasing. So here, for example, we have Daimler-Benz. So here we have a job announcement that they're looking for a system engineer with 3 to 7 years on hands-on experience with model-based system engineering. Coming to Porsche. So they published a statement in 2022 that they want to change their technical development. And they say, okay, it can only be done with introducing system engineering to realizing highly complex systems. as well, we have Audi. So we have here a statement from Jan Mikkel. I think he was the technical leader. He says, if someone didn't understand system engineering at this certain point of time, he will have problems in the automotive industry, because this is not a new topic here. It should be very let's say widely spread within the automotive industry. Another statement here from Volkswagen. So it's also from 2022, which relates to the Porsche statement. This is about talking about shorter development cycles. And with systems engineering, they say, okay, you can reduce the development cycles by roughly 25%. Another one from Volkswagen, they have some job announcements here. This was in 2023. And they're looking for a system engineer who is responsible then for the functional supervision. This is also the interdisciplinary aspect here. And represent the system externally in committees regard to other systems. So if you want to present this in a committee and talk about with external partners, then you really need to have a big picture and a good overview of your system. And last but not least, we also have BMW here. They joined the Center of System Engineering with RWTH Aachen. This is the university, and they have here Allianz, or you can say, or this is a new member. So we also had a look at some social media aspects. So what is the impact of system engineering at the moment? And we investigated platforms like Xing, LinkedIn, Stepstone, Jobware, and also Incozy. So Incozy is the official, let's say, it's the International Council on System Engineering, so it's the official authority. This was the word I was missing. So it's the official authority. And in Germany, we have also a sub-authority. This is called the GFSE, so Gesellschaft für System Engineering, but Incozy is global. So take a look at the members. And I just want to point out that you need to be sensible with these numbers, because when we searched for that, we don't have any, let's say, insights how they stick the word systems and engineering together, or even just engineering and then combined with some other aspects here. So, but this will give you a good overview. So Xing, we found that plus 10,000 people, they have the qualification system engineering in there, or let's say some other combinations between system and engineering. And LinkedIn, which is globally, it was 4.1.9 million. And in Cozy, this is a really reliable number. This is 23,000 plus. And these are members, and I'm pretty sure they are all, let's say, qualified members. So you can do also on the system engineering a qualification. They have several levels here. When it comes to job offers, and again, we don't have insights about the combinations here. We found out that on Xing, we have roughly 5.7 thousand jobs. On LinkedIn, 4.1. The biggest number we found was on Stepstone, with currently 53,000 jobs to offer, and Jobware is 2.9. And with that said, we come to another topic, and I will hand over to Sebastian again.
Okay, thanks, Alex, for the introduction, or for the overview over the systems engineering. That's very interesting. And in the last part of the webinar, I will give just one small example how to improve the, let's say, speed of development, for example, how to get a possibility there. And this would be the so-called digital twin. That's part of the model-based systems engineering. Maybe one or two of you or everyone has already heard about the digital twin. In general, it's described very easy. The digital twin is a simulation of your component. So in the physical world, sometimes it's complex to get a prototype, for example, to get the system done, the system completed. And so you generate a digital twin to simulate your component. This has lots of advancements. In general, you don't have to get to the physical system. You can do some tries with it before. You can change parts of the system more easy than in a physical part. You can use it to analyze what impact is there on the system for various situations, not only changes, but let's get to another point in testing, for example. You can reduce your cost because you don't have to get all time a new prototype if you want to see some impact. You can get through this to a faster time to market. So if you can simulate impacts, you don't have to wait until you got a new prototype, you got a new prototype tested. So it will improve your development speed. Also, you can get a higher variability. You can try in your simulation several possibilities, several in mechanical parts, several materials, or in electronics part, several different possibilities to configure your device, your component. And this will lead to a higher quality because you know more influences in an early stage of development. You don't have to wait until the late stages with impacts you will see and you will know. Also, you will get a higher grade of automation because, as I mentioned, you can simulate very much, and depending on the let's say level you are with your digital twin, you can simulate very much. But as you see in the red parts, it's not the real environment. It's a simulated environment still, and so it's not possible to replace everything. So you will need some physical parts, for example, some systems to finish your testing, for example. It will be necessary, but you can improve it. You can predict some of the tests, of the results, for example. And another point is, of course, if you think about it, you have to know it's an initial effort to implement those digital twins. You have to program your surroundings, your environment, your simulation. But in general, it's a good possibility to get faster to the market and to see impacts of the other components of other surroundings very early. So it's just one example, let's say, what is possible to or through the systems engineering, and it's far more. It's just one of the examples. Yeah, I think we're already nearly done. So in general, what did we talk about today? The development is getting more complex, more functionalities, more distributed, and we need solutions to solve those issues or these challenges. If we don't solve it, we will get very high budgets that are necessary. The schedules will explode, the resources will explode. So we need a new approach. And that's shown with the systems engineering. As we already saw, and Alex shows us, is that demand for the systems engineering is increasing. We saw from nearly all big OEMs in Germany that they want to use systems engineering. They need people that do the systems engineering because they already mentioned, like Alex already mentioned, they know it is necessary. And the systems engineering means in the end to take over the responsibility and to find the solutions for the complexity, not only for the development itself, but also for the challenges that comes for the organization. Yeah, there are various methods from systems engineering, and so you can use it for various challenges in the development and in the strategic approach. And for future development, as Alex already said, you need a strategic approach, and that's or that can be systems engineering. It's not the only solution, but it's a good solution. And if you want to know some more about the topic of systems engineering, Alex already mentioned in the introduction. In June, we will do a training, and there will be points like how do I trade requirements, for example, how do I get to an architecture, how do I trade the testing levels, and this will be done in a deep dive, not just an overview like we did today. It will be a deep dive of a few days. So if you're interested in it, you can see on our homepage, or you can also contact Alex or me whenever you want to this topic. So I think that's it from our side. Alex, from my side, thanks to you for the introduction of systems engineering, and thanks to all of the participants. And I think now we can join into the questions. Maybe Alex, did you already screen if there are some questions?
Yeah, so thank you, Sebastian, for the conclusion also. We already have one question from Paolo Massari, and now you are also welcome to unmute yourself, but I'm going to read it out loud. So what is, in your opinion, the best rule when we need to define system granularity from the system to the subsystem to the components, when to stop? This is a very good question, Paolo, and there is no, let's say, explicit answer here. The classical consultant answer would be depends. Here it is. You need to handle the complexity on each system level. When you have the feeling that you can not handle it anymore because you have too many components on one level and you have too many interference, then it would make sense to split it up and have another subsystem in here. But I have one hint for you. So there is a rule of thumb, according to some experts, according to the system engineering handbook, and this say that for each level you should have, let's say, 7 ± 2 elements to make it handle, to make it good handling for the complexity. This is something which I found in the literature.
Many thanks. It helps. It is like a rule to do not have like an exponential then at the end of the day number of.
Yes. So this is only a rough target value. So 7 ± 2. Of course, in reality, you really need to investigate if you can still handle the complexity and what are your, let's say, architectural goals. We have several architectural goals. Are you concentrating on make it modular, the architecture, make it really secure by design? This can also have an impact on your system development here. But thanks for the question.
Many thanks. I have another question, if it's possible. If there are no other questions. You've said several times that a big challenge in the new system engineering world is the communication between the interfaces. Do you see where is in your opinion, the highest risk within the communication? So you mean risk communication, or maybe communication for the developments or requirements, or communication about anything else? So what is your experience, or the highest risk in the communication?
So as a system engineer, you should have a good overview, a good picture about all domains, how they operate, what are their activities are. So we have several risks when it comes to first of all, requirements management. That, for example, requirements from system level are not correctly understood and interpreted on software, hardware, mechanic, for example. So this is one big risk, and this can lead to a different, let's say, architecture development, and not according to the customer need. Another aspect can also be the timing aspect, that they specific domains only look at their, let's say, timing, and don't have a look at the other domains. What are my impacts? So if I start a test case very late, so then the next possible development cycle can be delayed. And these are some timing aspects which comes also here in place. And actually we have many impacts. So it's not only one, it depends on the viewpoint you're looking at.
Okay, many thanks.
Okay, thank you, Paolo. Do we have some more questions? We are already close to 5, but maybe we have another possibility for a short question.
Yeah, Alex, actually, I could not join the session due to the clash. So, heard on the YouTube for the recordings. I mean, it will be uploaded after 2 weeks. I would appreciate if it can be shared for the attendees.
Sure.
Yeah.
Sure. We gonna upload the whole recording on YouTube, and you can find the posting on our website, and we also publish the slide set.
Yeah. Thanks, Alex.
For deeper, let's say, reading, and yeah. And like Sebastian said, if you have further questions or are curious now, what are the contents of our system engineering training, you're very welcome to join in June, and then we jump into some more details, because this was only a rough overview. Okay, then I would like to thank you all for participating, and I hope you enjoyed it.
All right, thank you. See you then.
Thank you.
Bye.
Thank you.
Bye.
Have a nice day.
Bye.
You are the pioneers. With your visions, your ideas, and your passion to make things better. And we are the ones who protect you from pitfalls. We are by your side whenever needed as a true fellow. Reliable, pragmatic, realistic. Together we make your product come alive. Imagine you enjoy improvement. Process Fellows.